2019. Today we're going to talk about the relay pumping setup criteria. And typically one of the things that we want to look at when we're setting up a relay is we want to know what our tactical objectives are. And our operation is going to be setting up determining the number of engines, and then determining the spacing, and then determining how much hose we need and or appliances to do the job, and then report that back to either our task force leader or the incident commander of the fire. So with that, let's go ahead and start. What I'm going to do is I'm going to cover everything initially. I'm going to do a dry run, and then when I get done with that, we're going to go in and we're going to actually set up the math so that you can see how it all comes together. So for long-range relay pumping operations, where do you begin? How would you determine the number of engines and where to place them, and then what's the process? So the process begins with the first 5 things here that you see. Number 1 is to determine the flow needs like anything else. If you're going to set up a progressive hose lay, you need to determine your flow based upon the number of nozzles that you have out there and what type of nozzles those are. So likewise, we need to determine the flow needs if we're going to be supplying a pumping operation, if we're going to be supplying laterals, or if we're going to be supplying a helicopter dip site. So that's what we want to do first, is determine the flow. Secondly, we need to determine our starting elevation as to where our initial pump is going to be placed. Number 3, we want to determine the final elevation. And for both of these, for number 2 and 3, you can use a map or a GPS or whatever you have available. Just try to be as accurate as possible. And then number 4, you want to determine the total distance between the 2 points from start to finish. This is a process of close estimation, and you want to round to the nearest 100 feet. You want to be as accurate as you can with this, because as you start moving your gallons every minute through this hose, you're going to have friction loss to contend with. So you want to be as close as possible. And then in number 5, you want to determine the initial engine pressure required. And what that is you do your friction loss calculation like you would for a standard hose lay. Then, once you've got the determination of the initial engine pressure, the friction loss plus the head plus the nozzle. This tells you how much pressure is needed to do the entire job or the task that you have been given. So you want to take that number. And don't be surprised if it's an enormous number if you got to go over several thousands of feet of hose. Then you'll use the formula for determining the number of engines, which is a modified pump equation, but includes SP for safe pump pressure reachable by all engines. I like to use 225 psi for the Type 4 and Type 6 Wildland engines. Then, continuing on, you'll want to figure up your target elevation, which is the highest point above your pump that you need to get the water to, and then subtract your start elevation from this. So as you see here, your head in feet is going to be the elevation, which for this example is going to be 6,445 feet. We're going to subtract our starting elevation of 5,526 feet, which gives us a head in feet of 919. Then we'll take the 919 and multiply it by that 0.434 to get 398 psi for our head pressure. Then you'll next take care of the friction loss. The relay is going to be spread out over 2.42 miles, and then what you'll do is you'll multiply that number by 5,280 feet in a mile to get the total distance of 12,777 feet. Then, because hose comes in 100 feet, you have to figure out what the number of sections are. So take the 12,777, divide it by 100, and you get 127.77 sections. So then what you'll do is you'll take the 127.7 and multiply that by 12.6, which you would obtain that number if you were using a Cascade Fire nozzle discharge calculator, and that is the friction loss for flowing 60 gallons a minute through 100 feet. we're going to use 60 gallons a minute, and I'm going to show you why we're going to do that as we move on. But like I said, I'm giving you the numbers now, so that way when we do them, you'll understand the methodology and the process that I'm using. So continuing on, the nozzle pressure is going to simply be 100 psi like normal. We're just going to leave it right there. The friction loss total is 1,609 pounds. The head is 398 pounds. The nozzle is 100. If you add this all up, you get 2,108.74 pounds. So total required for this 2.42 mile relay operation. That is the total. That's our initial engine pump pressure. So this is what we're going to be supporting, is a helicopter dip tank. And this tank here is a 6,000 gallon tank. And the helicopter that we've got is a Type 3. And it carries what we're used to out here in our corner of the world is a 180 gallon bucket. So now, if you remember, I said that the first thing that we need to do is determine our flow needs. Well, we can arbitrarily say, oh, well, we want to flow 50 or 60 or 100 gallons a minute, but we don't know if that's going to work. The reason we don't know if it's going to work is because we don't know what the helicopter's round trip time is going to be. So that's what we got to do. We got to figure out what his round trip time is going to be, and we can do that by asking somebody, or we can physically time it. But it's usually better to just sit here and figure out, hey, ask the pilot, what's it going to take? If he says, oh, well, you know what, I can fly there and back about 3 miles there, 3 miles back, I can do that in about 4 minutes, well, then we know that we've got something to work with now, because if we take the 180 and divide it by 4, this equals 45 gallons per minute, equivalent fire flow. So now that gives us something to work with. We have to know, we now know that for our relay operation, we have to supply at least a minimum of 45 gallons a minute to make sure that this thing works. So, if we move on, we can see our map now, and we know that, okay, a task force meets up with us. We look at this and we go, okay, where are we setting this tank up? So, the task force leader comes over and says, well, we're going to set this tank up over here, and we'll put an X in it to signify that that's the dip site. And where you're going to get water is 2.42 miles away, and that's all the way over here on the left. So at that point, you now have your map, you now know what you got to do. Now it's time to actually go to work. So like I said, the first two things that we've done is we've determined, number one, the flow. We know that we've got to have 45 gallons a minute, and we have to determine now our target elevation and our starting elevation. So since the starting elevation is almost always going to be the fastest one to obtain, because that's where you're most likely going to be parked at initially, it doesn't matter which order. So we know from this that the start elevation is 5,526 feet. And if we look on the map or use our GPS or have a crew member, whoever, up on top of the hill, they can give us a GP altitude, and they do, and it comes in at 6,445 feet. So, if we move on with this, now what we want to do, we take our head and we take our 6,445 and we subtract 5,526, and if we do the math, we can do the 15, we've got 9, and then we can calc this out. This is going to be a 3, a 1, a 5, this makes this a 14, a 9, so 919 feet. Now, that's our head and feet. What we have to do is convert this to a working number. So we've got to get the pressure required to raise the water from our start point to our end point. So, normal friction loss calculations when you're working with portable pumps or simple or progressive hose lathes, they usually tell you take the elevation divided by 2. But when you get into high elevations and long distance pumping, I like to use the absolute numbers. And I'll show you why now. So let's take our 919 and let's divide that by 2. If we did that, we would get a number that equals 459.5 psi. So we'll just keep it at 459 psi. So now if we take this same number, 919 feet, and we multiply it by 0.434, we get 398 psi. Well, that's a difference of 61 psi. That's 61 psi that if I had to string out extra hose, I could get an additional 400 feet of hose out there by doing it this way, if I had to. Or I could use that 61 psi and maybe boost the flow a little bit more. If you remember this picture of this guy right here, if something blows up there and they need to put a portable pump on the back side of this tank and start pulling water out to support this operation, they'll now have it. Whereas before, we would probably be at our maximum limits and not be able to support that. So I like to leave the options open, and that's another reason why I like to use absolute numbers where possible. So the head pressure requirement that we're going to go with is 398 psi. And we'll say that our head equals 398 psi. So now what we need to do is we need to work on our friction loss. And in order to obtain that, we need to get the total distance first. So, like I said, we can continue on, and if we use the software, it tells us that our distance from start to finish is 2.42 miles. So, the first thing that we need to do is take 2.42 and multiply it by the number of feet in a mile, which is 5,280. And if we do that, we come up with 12,777. So now we need to convert that 12,777 into the number of sections that our fire hose comes in, which is 100 feet. So if we take the 1277 and divide it by 100, we get 127.77 sections. That's what matches the first one. So now we got the total number of sections. Now what we would do is we would either use our IRPG, and we could, on page 87, it shows that the friction loss for 60 gallons a minute is 15 psi. I'm not going to use that number. I'm going to use 12.6. But let's show you once again what would happen if we were to use the 15 and multiply it by the number of sections. We would have 15 times 127 equals 1,915. But if I use the actual coefficient for the hose diameter, based upon the flow, I get 12.6. So if we multiply that out, we get 1,609. If we do the 12.6 times 127.7, we get 1,609. That's 300 psi difference. That's the difference of rounding up versus using the actual numbers. So that 300 psi, that's the difference of either 690 feet of elevation gain, or that 300 psi could be the difference between extra sections of hose. So, if I save that, that means I could conceivably throw out an additional 1,000 feet. Easy. So, it pays to use the actual numbers. So, the number for the friction loss that we're going to use here is the lowest one, which is 1,609. So, We've got our head pressure of 398. We've got our friction loss now of 1609. And we know that we were using our nozzle pressure of 100. And if we add all this up, we get 2,108. So now we've got the engine, the initial pressure number that we were setting out to get. Now, if we go back to the number of engines, which is what we got to find out now, that number we just got, the 2108, if we divide it by the number of pounds per square inch that every engine has to reach, which is 225, and we divide those two, we will get the number of engines, which equals 9.37. So the number of engines equals 9.37. So we now know that along this line, we're going to have nine engines. So now we need to determine the spacing. The spacing comes down to the distance divided by the number of engines. And we don't have to worry about the head pressure in between each engine because it's already been taken care of when we did the friction loss calculation because we included the head pressure. 12,777, and we divide it by 9.37. And when we do the math, equals 1,363 feet. This is where, since it comes in 100-foot sections, I don't think that I would go any more to 1,400 feet. I would drop this down to 1,300 feet and then adjust my pressure, but you're going to try to pump to the 225 psi. That's what you're going to go for. So what's nice about this also is that you can see here that we have a nice slope profile. So with that, I hope that answers the questions on how to set up and what you're looking for. I don't think that I would shortchange anything, but this is the basic. This is what you want to look at. 2.42 miles is not a problem. You're pumping 60 gallons a minute up 1,000 feet of head, 2.5 miles away. You can do it with 9 engines. You can do it with 4 engines. The only downside is that if you use 4 engines, you need to double the amount of hose. So instead of having 2.4 miles of hose, you're going to need probably 4.8 miles of hose. You're going to need double the amount of hose. That's the only downside that I see.